I'm going to talk a little bit about substitution reaction mechanisms today, and specifically the way that the Sn1 versus Sn2 mechanism occurs. So before I go over this, I want to just review what happens in a substitution reaction. And so in a substitution reaction, specifically, it is an organic molecule and there is a leaving group. And the leaving group has a tendency to leave the molecule when it is displaced by a nucleophile. And so some of the requirements that help a substitution reaction occur are that the leaving group, this bond here, is able to be broken, and in order for it to be a substitution reaction, the leaving group, whether it be one atom or a group of atoms, it leaves with the electrons. That leaves behind a carbon that still needs one bond, and in order to have a bond you have to have electrons. And so the nucleophile has a pair of electrons that is available to form a bond, and it would like to form a bond. And so in one of these reactions, what will happen is the leaving group will leave and it will go off by itself, and it will be replaced or substituted by the nucleophile. And the pair of electrons that the nucleophile had available to form a bond will form the new bond, and the carbon will still have the other groups attached. So these R's are just whatever random atoms. Usually those are other carbons or hydrogens, things that have stable bonds. So carbon-carbon bonds are stable, carbon-hydrogen bonds are stable, and do not get replaced by other atoms. So this is the overall look of a substitution. How it occurs, how it goes from having the leaving group attached to the organic reactant to having the nucleophile attached at the organic product, that is called a mechanism. And we have been doing reactions and showing the way that they occur by using curved arrow notation. And so we're going to go through the two types of substitution mechanisms. And these are referred to as Sn1 and Sn2. They both have in common there's a leaving group and there's a nucleophile. And so the reason that one of them is called Sn1 is it is a first order reaction. It occurs in at least two steps. But it's considered first order because the organic substance is the one that limits the rate. And so if it has a really it takes a long time for the reaction to occur, it is because of the organic substance, not the nucleophile. In Sn2, the nucleophile is replacing the leaving group all in one step. So it is a one step. So this 2 and 1 is not the number of steps, it is the order of the reaction. So I have an example to go through, and I have chosen a substance that has the same formula as the other substance that I'm going to compare it to. It's just that they are isomers of each other. And so some of the things that are really important in order for you to predict what mechanism occurs are the kind of leaving group. And so for a good reaction, a good substitution reaction, whether it be Sn1 or Sn2, for a good substitution reaction to occur, the leaving group has to be a good leaving group. What makes it a good leaving group? whether that bond is weak, whether when you form the leaving group by itself that is stable. Those are two of the things that affect the ability for this group to leave. The other thing that affects the reaction is the kind of nucleophile. And so usually ionic substances are better nucleophiles because the anion will have a pair of electrons and it'll be negative. And so if it is an anion, then it has electrons available to form a bond. And so if you see a metal and then a polyatomic ion or a nonmetal, then you should cancel out the spectator metal and you want to replace it with the formula of the anion. And so I'm going to draw in this, I'm going to draw the OH and I'm going to put the electrons in it. Okay. This nucleophile is a good, strong nucleophile, which means that it will form a good bond. So if you have a good leaving group and a strong nucleophile, then there's a good chance that a substitution reaction will occur. What kind of substitution reaction is the different mechanism? And so what helps you figure out, the last piece that helps you figure out which mechanism is the kind of carbon that the leaving group is attached to. And this carbon here, it is carbon number 1. It has a leaving group on carbon number 1, and this carbon is only bonded to one other carbon. So this carbon is considered a primary. And so our iodine, our leaving group, is on a primary carbon. If you have all of these things present for a reaction, so you have a strong nucleophile, so that's going to be good, a really good leaving group, that's good, and it's primary, then this reaction mechanism occurs via Sn2. So if we just look at what the product is, then all substitution reactions, the leaving group leaves with its electrons and the nucleophile takes its place and uses one of its pairs of electrons to form a bond. So I'm just going to draw the product and then I'm going to show the curved arrows that get us to that product. Okay, so leaving group leaves, nucleophile takes its place on the same carbon, everything else looks the same, and your leaving group is by itself with all of its electrons plus the electrons from the bond. So the mechanism is how this occurs. And so the mechanism occurs via an Sn2. So what that means is that both reactants are forming bonds and breaking bonds in the same step. And so this oxygen here comes in and goes after the carbon that has the leaving group. And so you draw an arrow from the, always from the electrons to where it's going. So here's a pair of its electrons and it's going toward the carbon. In order for it to form this bond, the iodine has to break its bond and leave. So here is the leaving group, and here is the nucleophile. And so here's the mechanism. The oxygen electrons come in bond, and so there's the electrons there. I drew them in pencil. And so this bond now is from that pair of electrons, and oxygen still has its other two pairs, and it still has the hydrogen attached. The carbon still has the two hydrogens attached and the rest of the carbon chain. And iodine has its three pairs plus the pair of electrons that it was using to bond to carbon, and there it is as iodide. Sodium ions are still present in solution, but they're a spectator, so I've kind of just crossed them out of the reaction. The reason that this can occur is due to the ability of your nucleophile to actually get to the carbon. And so here is a model of this molecule. And so carbon 1, 2, 3, 4, 5, 6 with all the hydrogens, and there's the iodine right there. So right there's the iodine. And so this carbon here is bonded to one other carbon, and it has the hydrogens present. And here is the hydroxide. And so here's the pair of electrons. And so this oxygen can easily get to this carbon. And so it has to be able to get to the carbon in order to form a bond. Because if it can't get close enough to the atom to form a bond, then it's not going to form a bond. And so as this oxygen comes in with its negative charge, it wants to bond to this carbon. And in order to bond to this carbon, this bond here with iodine starts to weaken, and it causes this bond to break and iodine to go off by itself and the oxygen to bond to it. So then you end up with the alcohol. And so we go from having one iodohexane to one hexanol. So this is an Sn2 reaction. So 2, again, means that both the nucleophile and the organic substance with the leaving group, that they are reacting in the same step. As one bond forms, the other bond is breaking. The other mechanism that can occurs in two separate steps. So an example of a substance that would form in two steps is 2-iodo-2-methyl pentane plus, and I'm going to change the sodium hydroxide to water. Okay, so when this occurs, there's a few differences in this reaction. And so we still have the same nucleophile. Our nucleophile is the oxygen from the water molecule. So the oxygen has hydrogens on it, and it has lone pairs. And the oxygen is partially negative. Hydrogens are partially positive. Okay. So when water is the nucleophile, eventually you will get an alcohol because the oxygen will bond to the carbon. But it occurs in a slightly different set of steps. We still have a good leaving group. So here is the iodine, here is the carbon. And so water, it is a moderate to weak nucleophile. you have a good leaving group, and you need a good leaving group because you need that bond to break. Okay. When you have this moderate to weak nucleophile and a good leaving group, the last piece of the puzzle to think about is what kind of carbon is the leaving group attached to. And so this carbon is bonded to 1, 2, 3 other carbons. So this is tertiary. And tertiary, when it is tertiary, the carbon is bonded to other carbons, and it's going to make the reaction occur via an Sn1 mechanism. So if we just look at the beginning to the end, this is our leaving group. The O with one of the H's is going to be our nucleophile. And so our final product, no matter what the mechanism, if it is substitution, our final product will be the leaving group being gone and the nucleophile bonded to that same carbon. And then your iodide. But then you also have that hydrogen that was not a spectator. Okay, so there is the hydrogen that was part of the water. Okay, so how does this reaction occur? It's going to be slightly different. And so it will happen in several steps. So the water doesn't come in and bond at the same time that the iodine leaves. The first step in an Sn1 reaction is the leaving group leaves. So what does that look like? Well, to show this leaving, this bond breaks. And so if this bond breaks, just like this, we're not going to show the water coming in yet because it doesn't come in yet. This is the first step. So the first step, this bond is going to break. And so we're going to end up with everything still attached except for the iodine. Okay, so it's bonded to this carbon here. So this carbon now no longer has that fourth bond. When a carbon only has 3 bonds, it is a cation. So we form a tertiary carbocation. Carbon is not something that usually wants to be positive or negative, but it can be. When can it be? The most stable times, one of the most stable times that it can become a carbocation. This is temporary, but it can become a cation if the carbon that would have the positive charge is tertiary. The other thing that helps stabilize this is if you have a polar solvent that can form hydrogen bonds, because hydrogen bonds are the most polar of the intermolecular forces. And so we studied this in general chemistry too, intermolecular forces. So water forms very strong polar intermolecular forces. And so for this substance here, water is present in this reaction. And so water is going to help stabilize this carbocation. And I'm only drawing it two-dimensional because I don't have enough room, but it would be surrounding it on all sides. So the oxygen is partially negative, and it's going to be attracted to the carbocation. And so there's going to be an ion dipole intermolecular force. Ion dipole intermolecular force. That helps stabilize it. And why it's important to be stable is if it's not stable, it will not form. You do not have reactions that create things that cannot be stable. So if the reactants are more stable, they'll stay the reactant and they will not react. But if you can form more stable products than you would predict, then this has the ability to form. Now, this is a very slow step. So this is actually the reason that it's called a first order reaction, because this step in the mechanism is the one that's the slowest. So it actually occurs in equilibrium. So this step to this step, I'm going to draw the equilibrium arrows. It's constantly going back and forth. The iodide that is still here, now it's actually negative, and so it also is attracted to the positive carbon. So we have the water molecules and we have the iodide. Both of them attracted to the positive carbon, and so it's constantly going back and forth. So you have water and your tertiary iodine molecule, and it's in equilibrium with still the water, this substance being aqueous, plus iodide. Some of the water molecules along the way, as this forms, if the water gets close enough, the oxygen can form a bond to this carbon. And so to show that, you would just show an arrow, because dotted lines would just be intermolecular forces, but an arrow would be this thing is going to bond or a bond is going to break. And so if some of these water molecules actually form a bond, then we get the next step in the reaction. So I'm going to draw it going down my paper. And so the carbon, all the carbon atoms are still the same. But now this water molecule is attached. So that was water being attached. Now oxygen has 3 bonds. So oxygen's positive. Iodide is still present. And so this is the next set of products that forms in this mechanism. This negative is attracted to the partial positives of this water molecule that's bonded. So water only wants to form 2 bonds, so it's got 1 too many. The bond to the hydrogens is the weakest. Now this new bond to carbon is pretty strong, but the weakest bonds would be the bonds to the hydrogens. And so the iodine will come and help remove one of the hydrogens. This bond between oxygen and hydrogen does not take the electrons with it. Hydrogen will leave the electrons behind, and so they will stay with the oxygen, and you will end up with our final product. So our final product, the organic molecule, but now you have the OH bonded, you still have the iodide, and the hydrogen now is off the water. So again, here's the step right before it. Some of those water molecules that were attracted to the carbon from a bond. The hydrogen will come in, or the iodide will come in and take a hydrogen. The electrons, I better draw a better arrow. Positive there. This bond will break. The electrons stay with the oxygen. The hydrogen comes off. And it will then be attracted. This bond will not completely form, because when hydrogen and iodine are in water, it's a strong acid, and so that bond does not form. So, but they are still going to be attracted to each other. So then you've got this OH now bonded, which was the original thing. If you go all the way back to the original, that's the leaving group. The nucleophile will be the OH portion of water, and so the OH will replace the iodine, and you'll end up with iodide off the molecule, hydrogen off the water molecule, and the OH bonded in place of the iodine. What we just went over was the various steps that occur. So just to review real quickly again, the Sn2 mechanism, primary carbons, good leaving group, strong nucleophile. The reaction happens all at once. One bond breaks as the new bond forms. So you directly make your product. Sn1, it's called Sn1 because it's a first order reaction. The thing that slows down the reaction is the leaving group leaving. The leaving group leaves when you mix the reactants and that bond starts to weaken, but the bond breaks first to form an ion that is then stabilized by the polar protic solvent, which also in this case is our nucleophile, and oftentimes it will be the nucleophile. The oxygen portion of that nucleophile is what helps stabilize it. Those electrons are attracted to your positive carbon, but also your iodide is still attracted, so it's an equilibrium situation. When the electrons from the oxygen form a new bond, then you get not OH, but water now bonded to your carbon. And so now oxygen has one too many bonds, and the iodide helps come in and break the bond to the extra hydrogen, leaving behind the electrons to form the overall product that we predicted at the beginning. To show you what this looks like with a model, here we have the 2-iodo 2-methyl pentane. And so in one of these situations, the iodine will come off first, and it creates a tertiary cation. Now, a tertiary cation is trigonoplanar, but I'm not going to change models. So this still looks tetrahedral, but it's really trigonoplanar because carbon only has 3 bonds. It gets stabilized by still being attracted to the iodide ion and to the water molecule that is present. And so the water can come in and bond to the carbon, and eventually the hydrogen will break off of the water so that it can just form 2 bonds. Just like this. So you end up with your OH bonded to carbon number 2, and you have the overall reaction of the iodine leaving and the OH from water forming the hydroxyl group.